Greetings, everyone. In this video discussion, we will still talk about artificial intelligence, focusing on approaches in AI and typical intelligent system requirements. We will discuss first about approaches in artificial intelligence. An algorithm is a kind of container, and it provides box for storing a method or a functions to solve a particular kind of problem. It means that a single algorithm or a particular algorithm contains several methods or functions that is used to solve a particular problem. Algorithms process data through a series of well-defined states, processes or steps, wherein states do not need to be deterministics, but states are defined nonetheless. Algorithms must express transitions between states using a well-defined and formal language that the computer can understand. So this formal language is the basis for defining grammars of different programming languages. Um, okay, so I think you are all familiar with what we call formal languages, since it was being introduced to you in your subject automata and language theory. Okay, so in processing data and solving a problem, the algorithm where these states are taken from defines, refines, and performs a function. The function is always specific to the type of problem being addressed by the algorithm, because that's what it's supposed to be, creating algorithm to solve a specific type of problem, not creating an algorithm to solve multiple sets or different types of problems. The goal is to create an output that solves a problem. So the algorithm receives input that helps define the output in some cases, but the focus is always on the output. Since for us to create an algorithm, we must first know what should be our target output. And we have here 5 tribes that has a different techniques and strategies for solving those problems or sets of problems, resulting in unique algorithms. So the combination of this algorithm should eventually lead to the master algorithm, which will solve any problem. First, we have here the symbolic logic and symbolic reasoning. So the first two, both of these ancient tribes, the symbolist or the one who studies symbols, believed that knowledge could be gained by working on symbols or signs that stand for a certain meaning or event. But symbolic logic draw rules from them, while symbolic reasoning derived rules from them. So there's a big difference. The other one, since the other one is drawing or sketch or create rules based from those symbols, while the other one derived or decide or reason or understand rules based from those symbols. Next, we have here the connections are based on neurons of the brain. The connectionists are perhaps the most famous of the tribes. This tribe attempts to reproduce brain functions using silicons instead of neurons. Essentially, each of the neurons which are built as an algorithm that models the real world counterpart, each neuron solves a small piece of the problem, and using multiple neurons in parallel solves the problem as a whole. So instead, or for a single neurons, it will solve a small piece of the problem. Then, if you are having multiple neurons or multiple silicons, it will be used to solve a problem as a whole, or the different problems, or set, yes, or the whole problem itself. Okay, next we have here the evolutionary algorithms that test variation. So the revolutionaries relied on the principles of evolution to solve problems. In other words, this strategy is based on the existence of the fittest. So instead of survival of the fittest, it focused on the existence of the fittest, which means which means removing any solutions that do not match the desired output. So a fitness function determines the feasibility of each function in solving a problem. So using a tree structure, the solution method finds the best solution based on the function output. The winner of each level of development has to create tasks for the next level. Next is Bayesian approximation. So, a group of Bayesian scientists recognized that uncertainty was the dominant aspect of the view. Learning was not assured but rather occurred as a continuous update of previous assumptions that became more accurate. So this notion inspired Bayesian to adopt statistical methods, and in particular derivations from Bayes' theorem, which help you calculate probabilities in specific situations. So this Bayesian inference is an important technique in statistics, and especially in mathematical statistics. Next, we have here system learned by analogy. So, analysts used kernel machines to recognize patterns in the data. So by recognizing the patterns of a set of inputs and comparing it to known outputs, you can create a problem solution. The goal is to use equality to determine the best solution to a problem. It is kind of what we call reasoning that determines whether a particular solution was used in a particular situation at a prior time. Using that solution for similar situation rather should also work. Okay, so those are these different tribes which applies different techniques or strategies in solving problems that comes to come up with what we call unique algorithm. Those following techniques are somewhat being used in developing AI, since we all know that artificial intelligence systems are created to adapt or learn from its environment. They are not created to just do a particular task. Okay. So what are the different types of artificial intelligence approaches? So while everything seems green and sunny or seems easy to a non-specialist or ordinary users, there is a lot of technology to build AI systems. So there are four types of artificial intelligence approaches based on how machine behaves, and the first one is reactive machines. So these machines are the most basic form of AI applications. Examples of reactive machines are games like Deep Blue, IBM's chess playing supercomputer. So this is the same computer that beat the world's then grandmaster Gary Kasparov. So AI teams do not use training sets to feed the machines or store subsequent data for future references. Based on the move made by the opponent, the machine decides and predicts the next move. So it means that the machine is being adaptive to its opponent's move. Next, we have here the theory of mind. So this is where they are struggling to make this, or this is where they are struggling to make this concept work. So however, those developers or inventors or scientists, they are not there yet. The theory of mind is the concept where the bots or the what called robots or AI will be able to understand the human emotions, thoughts, and they how they react to them. If AI-powered machines are always mingling and moving around with us, then understanding human behavior is imperative, and then it is necessary to react to such behaviors accordingly. Next, we have here limited memory. So it means, or these machines belongs to the class 2 category of AI applications. Example for this one is this, or the perfect example for this one is this, what we call self-driven cars. So over time, these cars or machines are fed with data and trained on the speed and direction of other cars, lane markings, traffic lights, curve of roads, and other important factors for these machines to perfectly what we call operate or manipulate itself based on these traffic rules and regulations. Okay. Next is we have here the self-awareness. So these machines are the extension of the class 3 type of AI. So it is one step ahead of understanding human emotions. So this is the phase where the AI teams build machines with self-awareness factor program in them. So for example, when someone is honking the horn from behind, the machines must sense the emotion, and only then they can or they understand what it feels like when they horn someone from behind. So learning from experience. So based from what we called or based from this self-awareness. So that's it for this what we called approaches in artificial intelligence. So the four approaches in artificial intelligence. Okay, next. And now we proceed to the typical intelligence system requirements. With every intelligent system solution, there are what we call risk if it is not designed effectively. So to minimize risk, intelligent systems architecture needs to be crafted from a comprehensive solutions perspective. Even if only just adding an individual device to a current IT infrastructure creates challenges that the infrastructure was not designed to handle. So to help avoid these potential pitfalls, the following 10 areas should be addressed when designing intelligent system architecture. So first one is the security. Architecture and products must be designed with security in mind. Products and services must secure your data and keep out hackers. This is especially critical to your business if the data includes financial or payment card industry or PCI data or any personal data protected by confidentiality regulations. Next is we have reliability. So choose the field proven products that provides high reliability and stability. So because even more important is the ability to maintain each of the smart devices and the entire intelligence system architecture. So simply put, you do not want to build a system consisting of hundreds or thousands of devices is not which is untested or which is an untested technology. So you cannot just deploy a what we call system which is not tested for reliability. Next, we have here the scalability. Adding smarter devices to your current enterprise IT infrastructure without provisioning the IT infrastructure for higher traffic loads and device management means it is not likely you will benefit fully from the intelligent systems. Devices must be integrated into an architecture that addresses those issues and provides the needed resources. So it means scalability. You can add or the system is capable of recognizing or adapting to new technology or new devices being integrated to its system or to its infrastructure. Next, we have here this flexible, extensible platform. So having a single platform across the various tiers of an intelligent system architecture gives you business efficiency consistency and predictability. So consistency from the edge device through controllers and gateways and back into the data center makes development, integration, and maintenance much simpler. The next is we have integration with enterprise applications and infrastructure. So once the smart device data is received back at the data center and analyzed, the solution architecture needs to integrate with your current back-end business process management and data visualization tools. If the analysis tools for the collected data are not part of your business process or processes, new tools from independent software vendors or ISVs may be needed to improve business efficiency. So, for example, your data feedback loop might require tools for transformation from raw data, machine data formats, as well as additional tools to automate and analyze the output. Next, we have the system and device management. So being able to manage and maintain systems and devices is critical to maintaining stability, reliability, and security. So the architecture should provide for repair, replacement, and authorization of the complete solution, including devices, concentration gateway devices, and the data centers. Next, we have technologies that minimize work or minimize network cost. So power and the last mile connection of the devices and concentration gateways are significant cost elements in an intelligent system solution. An intelligent system solution needs to enter into and come back from lower power modes. It must also include low cost communication technology via cloud, internet, Wi-Fi, cellular, or enterprise local network connections. Older embedded devices typically respond only when pulled, but intelligent system devices report data asynchronously. So this leads to a significant increase in traffic. So many devices can store data for later analysis when traffic loads are too heavy for transmissions. Next, we have here the certifications. Choose solutions that already have the ISV certifications or the independent software vendors certifications and are compliant with appropriate local, national, financial, government, or regulatory agencies. Next, we have this stable technology product lifecycle. Mature or trusted products with a record of reliability and long-term product support can reduce the cost and complexity of maintaining a solution deployed in the field. And last but not the least is the maintainability. Older embedded systems often have a build it and forget it mentalities. Intelligent systems are dynamic and perform best when properly maintained. Devices must be updated, like for example, patches over fixes, security improvements, and new features and functionality that are needed throughout the service lifecycle. So an intelligent system designed automates as much as the update process is possible. Okay. And those are these what we call typical intelligent system requirements. So if you're gonna venture on AI development, make sure you take note of those several or 10 intelligent system requirements. And that's it for this video discussion. I hope you learned something from it. Thank you and God bless everyone.